Hi everyone, in today's lesson we're going to talk about trig limits. Before we do that, I just want you to take note of this trig limit flowchart that I have here. It's very similar to limits as we approach a number in that we're going to try direct substitution first. If we get a number, life is beautiful and we're done. If we get 0 over 0, that means we have a whole. Normally we have factoring, conjugates, common denominators, all those things to help us out of a whole. But if we have a trig limit with a 0 over 0, we want to use these, definitions. So the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of the reciprocal, x over sine x, also equals 1, and the limit as x approaches 0 of x over 1 minus cos x is 0. So these are pretty much definitions. I'm going to show you how they are true, but really I can just say memorize these and the limits will always be 1 or 0. So before we can do any of those, I want to show you trig limits with direct substitution only. So you will need a unit circle for this. So go ahead and pause the video and draw a unit circle and then hit resume when you're ready for the circle. So here's a unit circle. You should have had over here is the point 1, 0. Up here is 0, 1, negative 1, 0, and 0, negative 1. And it's helpful to also memorize the degree measurements. So here is 0 degrees, or 360. Here is 90 degrees, 180, and 270. It's also helpful to know the radian measures. So 90 degrees is equivalent to pi over 2. 180 degrees is pi. 270 is 3 pi over 2. And 360 is 2 pi. So that's definitely helpful to know as well. And lastly, it's important to know that the x value on a unit circle is cosine of theta. The y value on a unit circle is sine of theta, and the y over the x, or the sine over the cosine, is equivalent to tangent of theta. All right, so we're going to use this information to answer a couple of trig limits with direct substitution. So always, always, always with any limit, as we are approaching 0, we always want to try direct substitution first. So everywhere I see a 0, an x, I'm going to put a 0. So 2 plus sine of 0 over 3 plus x. Oh, excuse me, not x, 0. So 3 plus 0. So the denominator is actually 3. And the numerator, we just have to figure out what sine of 0 is. So you want to look at that unit circle you just drew. And 0 degrees is over here. So that point is 1, 0. So sine of 0 degrees is the y value. So the y value is 0. So this actually simplifies to 2 plus 0 over 3 plus 0. And 2 plus 0 is 2. And 3 plus 0 is 3. So my limit using direct substitution is actually just 2/3. All right, why don't you try example number 2 with direct substitution and see if you can get a nice pretty answer. And then hit resume when you're ready for the answer. Okay, so the numerator, we're plugging in 0 for x, so 0 squared plus 4. And the denominator, you should be plugging in 0 for x. So the numerator, 0 squared plus 4, is nothing other than 4. And in this problem, I'm asking for cosine of 0. So here's 0 degrees. Cosine happens to be the x value, so it's 1. So the bottom is 0 plus 1, which is 1. So 4 divided by 1 is 4. And that's what your limit should be. So these are two great examples of how I can have trig limits and use direct substitution only. All right, so now those other two definitions that I was talking about. So here's the graph of x over sine x. So if I asked you to find the limit graphically, as x approaches 0, you would check the limit from the left and limit from the right, and you would kind of just see what's happening. So the limit from the left, where is this graph approaching? And the limit from the right, where is this graph approaching? Well, it's approaching the same spot. So this is 0.25, 0.5, 0.75, and 1. So the limit from the left and the limit from the right hit the same exact value, and that value is 1. And you can even see there's a hole in the graph here, right? And the reason why there's a hole in the graph is because if you were to plug in 0 directly, 0 over sine of 0, well, we know that sine of 0 from before is 0. So you see how we get 0 over 0? That means there's actually a hole in the graph, which we figured out right there. But instead, we can see that even though there's a hole in the graph, the limit is approaching this y value of 1. And that will always be the case. Even if I flip it, the limit is still going to be 1. And I'm noticing here that there's a typo. I didn't actually flip this. So you want to write this as the limit as x approaches 0 of sine x over x is 1. So the same kind of concept will apply. We're still going to get 0 over 0, but the answer will still be 1. And here is actually the graph of sine x over x. So I know the graph's a little bit hard to see, but it's still doing the same thing. The limit from the left and the limit from the right are still approaching this hole here, this y value of 1. So it doesn't matter if it's x over sine x or sine x over x. The answer is still going to be 1. All right. So if I'm looking at these examples here, 1, 2, 3, and 4, we're actually going to use these two rules to evaluate the limits. So in example 1, we're going to x approaches a number. So we're still always going to do direct substitution. So the top is sine of 4 times 0 over 4 times 0. So technically 4 times 0 is 0. So it's sine of 0 over 0, which we know is 0 over 0. So check, we have a hole. So we know the only way out of a hole with trig is to use this definition. So we know that sine of x over x is 1. So sine of 4x over 4x, that answer is actually also going to just be 1. Because it really doesn't matter what is in here. As long as it matches what's beneath it, the limit will still be 1. So another example could be the limit as x approaches 0 of sine of 7x over 7x. It doesn't matter what is in here. As long as it matches here, 7x and 7x, this limit will still be 1. Right? Same thing as here, sine of x over x. As long as these two are the same, this limit will be 1. All right, so just for purposes of space, I'm going to do number 2 on a separate sheet. Feel free to fit it there if you can. So number 2 says, I want to find the limit as x approaches 0 of sine of 3x over x. So my first step is always going to be direct substitution, as always. So direct sub. So we have sine of 3 times 0 over 0. 3 times 0 is 0. And we know that sine of 0 is 0. So 0 over 0 means we have a hole. So now we're going to use the philosophy that the limit as x approaches 0 of sine x over x must equal 1. So like I said before, whatever is in this parenthesis needs to match in this parenthesis down here. So this needs to have a 3 in front, right, in order for it to cross off to be 1. So the idea now is going to be to do a little bit of manipulation with the fraction. So I'm going to put step 2, manipulate the fraction. So I'm just going to rewrite it. We have the limit as x approaches 0 of sine of 3x over x. And like we said, in order for this to cancel out to 1, we need this top and this bottom x to be the same. So this needs a 3. So a nice little trick that we're going to do is we're going to multiply this fraction by 3 over 3. And by doing so, you're multiplying it technically by 1. So the limit hasn't changed, right? We're just multiplying this fraction by 1. So now what we're going to do is do a little bit of, simplification. We can multiply fractions by multiplying tops with tops and bottoms with bottoms. So we're going to do that by saying, okay, we have the limit of x approaches 0 of 3 sine 3x all over 3x. So all I did was kind of just switch this 3 and put it in front. Multiplication is commutative, so I can do that. So technically, we have what we need. We have sine 3x over 3x. So this is what I like to call like a limit rule. And it basically says you can take the limit of this product in 2 separate pieces. So we could actually break this up as the limit of x approaches 0 of 3 times the limit as x approaches 0 of sine 3x over 3x. Now, I'm not going to ask you to break this up and write it every single time, but just know that that's really what you're doing. So technically, this limit is 1, and the limit of a constant is 3. So the answer to this entire limit problem is 3 because 3 times 1 is in fact 3. Now, if you were a little unsure as to why I said the limit as x approaches 0 of 3 is 3, here's the explanation. So the line y equals 3 is this line right here. And I want to take the limit as x approaches 0. So the limit from the left and the limit from the right are still 3. That's why the limit of this constant is 3. I know that was a lot, but the more practice problems we do, the better we're going to get at them. So let's try one more. So problem number 3. So I want to find the limit as x approaches 0 of 0 divided by tan of x. So direct substitution first. So 0 over tangent of 0. So we need to decide what tangent of 0 actually is. So remember, we're still on the unit circle. Here's the 0 degrees. So it's 1, 0. We know that tangent of theta is y over x or sine over cosine. So here's the x value and here's the y value. So if I want to find tangent of 0, all I'm going to do is take the y value, which is 0, and divide it by the x value, which is 1. And 0 divided by anything is 0. So that tells me that this is 0 over 0. So we have another hole. So our only way around the hole is going to be to simplify some things. So we already know that tangent of theta is equivalent to sine theta over cosine theta. So we can actually go ahead and replace tangent of x with what it's equal to. So we're going to do that by saying, okay, we have x on top, and then tangent, I'm just going to replace it with, instead of theta, I'm putting x, so sine x over cos x. And now just remember, we have 2 fractions that we're dividing, right? We have x and sine x over cos x. So we're going to keep, change, flip is how we deal with those fractions. So we keep the x, or x over 1. We change the division to a multiplication. And we flip the cos x over sine x. And now what you're looking for is one of the 2 rules that we talked about before. And I'm just going to write them down over here. The 2 rules are sine x over x or x over sine x. So we're looking for that because those limits equal 1. So I see one right here. I see x over sine x. So I know that multiplication is commutative and I can do it in any order. So I could rewrite this as x over sine x and then times cos x. And we're taking the limit of this whole thing as x approaches 0. So remember, we can take the limit of this product in 2 pieces. We can take the limit of this and then the limit of this, and then multiply them together. So again, you don't ever have to write it out this way, but I'm just going to show you. We're going to take the limit as x approaches 0 of x over sine x, and then we're going to multiply it by the limit as x approaches 0 of cos x. So here, this limit follows that rule up here. It's the x over sine x. So that limit, without any work, we know is 1. And in order to do this limit over here, the limit as x approaches 0 of cos x, that limit is just solved by direct substitution. So we're going to do whatever cosine of 0 is. So we look at the unit circle again, we look at the x value, and that cosine of 0 is 1. So we multiply these two together, and the limit is 1. All right, let's do the last one. So the last one says we want to find the limit as x approaches 0 of sine to the third x over 2x to the third. So first things first, we have to check direct substitution. So remember that sine to the third x is the same thing as saying sine x to the third power. Should have learned that in pre-calc as well as in algebra 2. And then this is just 2x to the third. We can leave it like that. So we're going to go ahead and plug in 0. So we have sine of 0, this whole thing to the third. And then we have 2 times 0, this whole thing to the third. So we know that sine of 0 is 0. So 0 to the third over 0 to the third. So again, we have 0 over 0. So we have a whole. So now we have to play a game of simplifying this. So another technique that we can do is recognize that we have an exponent. So sine of x to the third power is the same thing as saying sine of x times sine of x times sine of x, right? And then on the bottom, 2x to the third is the same thing as saying 2x times 2x times 2x. So what we're looking for is either x over sine x or sine x over x. And I think we actually have the first one. We have sine x over x. It's just kind of written in a weird form, right? We have this sine x over x, we have this sine x over x, and then we have this sine x over x. So we actually can break it up into 3 different fractions. So we have sine x over x times sine x over x times another sine x over x. And then if you realize what's left on the outsides is we've got 2, 4, or 2 times 2 is 4, 4 times 2 is 8. So we have 8 on the bottom and nothing on the top, right? So we actually can multiply this by an 8 and a 1, right? Technically there's a 1 here, right? So we could do 1, 2 times 2 is 4, 4 times 2 is 8. So each and every single one of these guys, sine x over x, when I take those limits as x approaches 0, each one of these guys, the limit is 1. So 1 times 1 times 1, and then times this last 1/8 would give me 1/8 as my limit. All right, I know this isn't the easiest of topics because it requires a lot of manipulation, so I promise we'll go over this a little bit more in detail in class tomorrow. So if you have any questions, please jot them down. All right, have a great night.